Okay, welcome everyone. Today, I'm very happy to announce our next seminar of the semester. Today we have Gabriel Marin, a member of our group. He made his bachelor's and currently he is a master's student here at the university. He's a member of our group, and the title of his talk is Celestial String. So please take it away.
Thank you, Vicente, for your very kind introduction. So, as you have already heard, I'm gonna talk about this story, which is titled Celestial Strings. So this was a work that we uploaded to the archive. You can check it out using that number. And this was done in collaboration with Lina Castiblanco. She's a postdoc at Newcastle University in the UK. Gaston Gabriel, he's a professor at New York University in the US. And Francisco Rojas, he is a professor at Adolfo Ibáñez University here in Chile. Okay, so here's the outline of my talk. I'm gonna divide it roughly by two. So on the first half, I'm gonna tell about this motivation and this proposal, which is titled the Celestial Holography Program. And I'm gonna also introduce why do we care about string theory in this context. And in the second half, I'm gonna talk about the celestial string setup in order to compute some additional nice computations. So particularly, I'm going to be interested in computing amplitudes. So how do we obtain celestial amplitudes? And I'm going to briefly discuss a little bit on how do we compute string amplitudes in momentum space. And then I'm going to finish it up by checking which is one of the main topics that we discussed in the paper, which is the field theory limit. All right. So let me start right away by telling you the motivation. So let me start by stating that a complete theory of quantum gravity remains to be one of the biggest puzzles in modern theoretical physics, where by saying quantum gravity, I'm just referring to any theory that explains gravity at a quantum level, but also it looks like Einstein's general relativity at long distances. So there has been significant progress in this topic in the context of a gravitational theory living on an anti-de Sitter spacetime, or just simply referred to as ADS, which is the spacetime corresponding to with a negative cosmological constant, where one can make a holographic identification to a lower dimensional non-gravitational field theory, which is actually a conformal field theory, or just CFT for short, living on the boundary. So this duality right here is well known as the ADS CFT correspondence, and was first introduced by Juan Malacena in the late 90s. So we can go on and ask ourselves, okay, do we have anything similar in the case of flat space? I mean, we can go even further and ask ourselves, do we have anything similar in the case of de Sitter? I mean, de Sitter is a very interesting spacetime that we all of us know it, and because of its cosmological importance. So but I'm not going to discuss anything about de Sitter in this talk. I'm just going to stay with flat space, which is a quite nice approximation of our world. Okay, so do we have anything can we say that we have anything as flat space holography? That's the question that we want to answer. Okay, so now in order to study this question, we first have to frame it into a physics perspective, right? So now in physics, we know that we're very much interested in observables. So if we were going to study a quantum field theory, one of the primarily observables are scattering amplitudes, which here you have a depiction of it in these double Penrose diagrammatics. So if you're not quite familiar with the Penrose diagrammatic, let me quickly review it. So here's the double Penrose diagram. So the blue lines correspond to the word line of massive particles, while these wavy red lines corresponds to the word line of massless ones. Okay, so now massive particles, they enter and exit this diagram at these 2 points over here. So little I minus and little I plus, and it corresponds to past and future time like infinity. So in the case of the massless particle, they enter and exit this diagram at these lines over here, corresponds to the big I minus and big I plus, referring to past and future null infinity. We verbally refer to these sections over here as scribe minus and scribe plus. You can then go on and study, okay, how can we parameterize these lines over here? So you can use these U and V parameters. So the V corresponds to the advanced times, and the U corresponds to the retarded times. Okay, you can then go on and further study, okay, what's the topology on these lines? And you're going to find out that they're composed of a real line times an S2 sphere, which is the one that we refer to as the celestial sphere. Okay, so now let me just say a huge shout out to this point over here. So little I0 corresponding to the space infinity. So there's a very nice set of antipodal matching conditions happening to the sphere. You can obtain them by studying what's the physics around this point over here. So yeah, just a really nice point to comprehend and to relate in and out states. Okay, so now I can roughly tell you what celestial holography actually means. So it refers to a duality between gravitational both scattering and the conformal field theory living on this sphere, this celestial sphere. So more concretely, we say that a four-dimensional quantum gravity is equal to a two-dimensional celestial conformal field theory, or just CCFT for short. So now we don't fully comprehend this dual description yet. We know that it has some properties of a conformal field theory. However, there are certain subtleties that we have to take into account. So yeah, this is why we don't fully write to the CFT. Instead, we add this extra C, referring to its celestial behavior. All right, so now let me answer to the natural question that could arise, which is, why do we actually believe in this duality? Now, in this talk, I can tell you.
Yes.
Sorry?
That was in AES.
No, it's in asymptotically flat spaces. Yeah, in Minkowski, if you want to take it. It can be done in some weird spaces that looks Minkowski on the boundary. But yeah, the more simpler case is done in just flat Minkowski. Okay, so let me answer to the question of why do we actually believe in this duality. So yeah, I can tell you about two hints in this talk. So the first one comes from the study of symmetries. So you can see that the Lorentz group in little d plus 2 dimensions acts on the sphere as the Euclidean conformal group in little d dimensions. So if we want to put some numbers, we see that the Lorentz group in 4 dimensions, which is the group that is describing us, acts on the sphere as the Euclidean conformal group in 2 dimensions. So the group of a 2D CFT. So there's a really nice set of matching symmetries happening. And so if you want to see it in a more group theory point of view, we say that the proper orthogonal Lorentz group, so SO plus 1,3, is actually isomorphic to SO2C quotientated by its center, which is Z2.
Sir, why do you have D equals 2 and not D plus 1?
So here?
Yeah.
Yeah, I'm here not referring to what's the temporal component. I'm just referring to the total number of dimensions that you have. So yeah, you can say that we have D plus 1 dimensions.
Okay.
Yeah. Yeah. Okay, so that's the first hint. And the second one comes from the study of the observables, particularly the S matrix. So from a long time ago, we know that if we want to describe some asymptotic states, let's say for massless particles, we can use we can describe them but by some energies and some points of the sphere, so Z and Z bar. When we do that, we say that we're representing the S matrix in the energy momentum basis. For instance, here I have a picture of it. So we have some initial data living on square minus. So these green lines, we have this scattering process happening on the bulk, and we have some external data at the square plus. So these are blue lines. Okay. So now if we want to study what's going on more effectively on this sphere, instead of using these energies, we use these deltas. So these deltas corresponds to the boost eigenstates living on the sphere. So when we do that, we say that we're working on the boost wave basis. You can then go on and compute for yourself and convince yourself that this delta is actually equivalent to the conformal dimension of a 2D CFT. So yeah, that's another reason why do we think that there's a 2D CFT living on the celestial sphere. Okay. So now these two bases, they're actually not disconnected from each other. You can go from one to another by performing this Marin transform. So it's essentially an integration over all energies. So an integration from 0 to infinity of d omega weighted by this delta. Yeah. In some sense, we're doing something similar in the same spirit of what we do in a standard KFT textbook courses. So in KFT, we usually start from a position basis, and then we move on into a momentum basis because things are easier to compute. So here we're doing something similar. We're starting from the energy momentum basis, and we're performing this transform to get to the pulse wave basis, or if you just want to call it, we can just say the celestial basis. Okay. So here's a small table of comparison of the two objects of interest in each basis. Of course, in the energy momentum basis, we're very much interested in computing standard amplitudes, which are given by the S matrix in this following form that I have over here. So now in the pulse wave basis, or the celestial basis, we're interested in computing celestial amplitudes, which are given by a correlation function of some operators that depend on the z and z bars and this delta. We also have these minus and pluses are just telling you the information whether the particle was incoming or outgoing. Okay, so now something really interesting about these celestial amplitudes is that they do have definite transformation properties under the global conformal group. So yeah, they transform these operators O, they transform very much accordingly as a 2D CF2. All right. So now at the level of symmetries, there's something really interesting happening. So of course, in the standard amplitude sector, we know that we have translation symmetry, manifest translation symmetry given by the delta function, right? So now in the celestial amplitude basis, we have instead manifest Lorentz symmetry, which is equivalent, if you recall the symmetry slide that I was showing you a couple of minutes ago, it's equivalent of having global conformal symmetry on the sphere. So yeah, there's a really nice set of symmetries going on this side over here, at least manifest. All right. So now there's a little caveat that I do have to tell you about these celestial amplitudes, and that's while they behave quite nicely, there are some weird features that are emerging. So for instance, there's a certain appearance of some kinematic Dirac deltas that are coming from the energy momentum conservation delta from standard amplitudes, especially when you compute lower point amplitudes, for instance, 3 and 4 points. Yeah, there's this distribution of behavior. So then you can ask yourself, okay, why is this a problem even to start? So yeah, you can recall your 2D CFT knowledge. If you don't have any, that's totally fine. So from a 2D CFT perspective, when you compute a 3-point correlation function, you can constrain it by using conformal symmetry up to a constant. So that's really nice. There's some really nice property that you can do in 2D CFT. So yeah, it's just up to a constant, and there's no appearance of any distributor behavior. So here we're seeing it. And there's also the issue that you could use a property from QFT, which is the operator product expansion, which is OP for short. So the OP essentially allows you to write down n-point correlation functions in terms of n-1 point ones. So yeah, this distribution behavior of lower point amplitude gets propagated into higher point correlation functions. So yeah, then you, I mean, there has been some attempts to solve the issue. For instance, you could use the amplitude. I mean, this is still a discussion topic in the community. However, if you just want to embrace it, like, okay, we don't have a 2D vanilla CFT, this is totally fine. But yeah, if you strictly want to have a 2D CFT, this is an issue that you have to solve. Okay, so now let me draw a really nice picture so we can have a better understanding of what's going on. So for a long time ago, we have been using the energy momentum basis. So here's depicted by this omega. I've been describing these new bases, this delta one, the pulse wave basis. Of course, I've told you that you can go from one to another by performing a Marin transform. So I have you over here. So yeah, you could insist of studying what's going on at the conformal boundary by just studying the position basis, using the position basis. So here it's represented by this U. So if you recall the Penrose diagram slide, it was the parameter used to describe scribe plus. So of course, position basis and momentum basis, they're related up to a Fourier transform, as I have here over here. And yeah, more recently, there's been the study that you could that showed that you can actually go directly from position basis to this delta basis, which is performing this transform, which is called the Lightbird transform. So yeah, it's essentially an integration over the U time weighted by this delta. Okay, so now there's a reason on why do we actually care on these 3 bases over here, that they're kind of like forming a triangle. So when you study low energy physics, or just IR physics, where IR stands for infrared physics, seems to be that quite nice to use different corners of this triangle over here. So this concept is this so-called, also referred to as the IR triangle. So the momentum basis, from a long time ago, we know that it's quite nice to study sub-theorems. The position basis, the memory effect, and where I'm gonna explain what's going on in the case of gravity, so we can understand what are sub-theorems of memory effects. And this top corner over here seems to be quite nice to study asymptotic symmetries due to these manifest symmetries that are emerging on these amplitudes that I showed you in on the last slide. Okay. So here's the example in the case of gravity. So we have the leading gravity IR triangle. So on the, let's start on the bottom right corner. So we have the gravitational memory effect. So this is an effect studied by Seldovich and Polnareff in the 70s, I think. So it refers to a memory-like displacement of two detectors due to the passing of a gravitational wave. So here I have a small animation on the topic. So suppose that we have an initial detector, circular detector with initial diameter g naught. So here's the gravitational wave passing through the detector. So it has an oscillatory behavior. And here's the final outcome. So you can then measure what's the final diameter, and you're gonna find out that's different from the original one. So yeah, in some sense, we say that the detector, the circular detector, remembers the gravitational wave. So yeah, this is a theoretical prediction. However, I think there's some hope to measure it in Project LISA. So this is the interferometer that's going out in space, I think in a decade or so. But yeah, there's hope to measure it experimentally. Okay, so that's the gravitational memory effect. We also have the bottom left corner, so subgravitational theorem. So it was first studied by Steven Weinberg in the 60s in the case of gravity. So it refers to a very nice set of factorizations going on the amplitudes. So imagine that we have an amplitude as I have it depicted over here, and we have an external graviton. So this is the wavy red line attached to one of the external legs. So the soft-graviton theorem states that if you take the energy of this external graviton to be soft, that is taking the energy to be really small, we obtain a really nice factorization, so consistent of a universal factor where you can extract really nice physics. For instance, if you impose gauge symmetry, you're going to find the equivalence principle in GR times the original amplitude is stripped from the ground. Yeah, that's the bottom left corner, and on the top corner we have the BMS symmetry.
Sorry, before you.
Sure.
How do you see them both of the same?
Sorry.
How do you see them both?
Both. Sorry. These. Oops. So you're referring to how do we see that the subgraviton and gravitational memory effect are the same? Yeah, you can actually compute a Fourier transform.
I know that, but
but in what sense do you mean?
well, in a physical sense.
In a physical sense, where the subgraviton theorem and the gravitational memory effect are the same. I don't know if there is any interpretation of it. I just know that it's a really nice calculation that you can do, that you can take the Fourier transform.
Yes, you're saying the Weinberg theorem is a factorization, the limit.
Mhm.
Maybe that factorization is the same as making the circle bigger or something like a factor.
Could be. I'm not really sure if there is any interpretation of this universal factor to translate that to the gravitational memory effect. Yeah, I'm not sure because you can only do that on leading order level, because when you go on and compute what's going on at subleading, you're going to have you also have some subgravitational theorems with a different universal factor. But on the right hand side, you don't have a memory effect. You have a spin memory effect on the gravitational waves.
Okay, but it must be a factor between the original diameter and the.
Yeah, but that's related to the polarization and the amplitudes of the gravitational wave. Okay. Yeah, but I don't know if that's, I mean, I don't know if that's, is there any interpretation to that to go into the subgravity, maybe some parameters of the polarization of these subgravity? I'm not very sure. Could be, I'm not sure. Okay. Yeah, thank you for the question. Okay, so now in this top corner, we have the PMS symmetry. So in the 60s, Bundy, Vandenberg, Metzner, and Sachs, they tried to answer to the question of what is the asymptotic symmetry group of asymptotically flat spaces and non-infinity. So they found out that it was not incorrect, which was the original naive expectation, because okay, they were working with flat spaces. So the symmetry group of flat spaces is just Lorentz cross translations, right? So that's just incorrect. So instead, they found an infinitely enhancement of this group, which we now call the BMS group, corresponding to these added symmetries, which are called super translations. So super translations are essentially translations that depend on the direction of null infinity. So here I have a picture of it. So for instance, let's say that we super translate the Richard time U. So we say that it's shifted independently at every angle on the scribe. So I here have a picture of it. So at every single point, the length of this arrow is different. And this is linked to this function over here. So if we had a typical translations, instead of a function, we would have just a constant. All right. So yeah, this is the story for the leading gravity IR triangle. And of course, this is not just linked to gravity. We also have the many more versions. So we also have the gauge theory versions. So we have a KD and Young-Mills one. And yeah, I've said it before, but we also have a subleading, this is more recent, the subleading version of the gravity IR triangle. So yeah, of course, and there's also the proposal that this could also apply to different areas of physics. So for instance, we could have something as the cosmological IR triangle. Maybe we can fill it up. And of course, there are many more versions, incomplete versions of this triangle over here.
Go. Can you go back from BMS symmetry to soft convergation theory?
Yeah, you can actually go. So yeah, you can actually see that they're related to what identities. So yeah, this is just symmetry applies to your amplitudes. You're seeing that from a QFT perspective that if you have some symmetries, it's kind of natural to think that you have some identities, which are the warbles. Yeah, you can go on and compute it explicitly. You can see that yeah, if you compute the wire energy of the BMS symmetry, you recover exactly the form of this universal factor times the amplitude. Yeah. Okay. All right. So now let me introduce the string parts of the chart. So let me start by stating a fact, which is that the tree-level four-point graviton amplitude in the celestial basis blows up in the UV. So here I have to be a little careful because if you recall the Marin transform, it was an integration over all energies, right? So it was an integration from 0 to infinity of the energies. Yeah, in some sense, when you talk about these celestial bases, the IR all the way up to the UV, they're mixed. So yeah, it doesn't make sense to say that it blows up in the UV, but here I'm just making reference to what is the exploding part, what is the infinity part of the interval. Yeah, so just stating that this is the infinity part that blows up. Okay. However, celestial string amplitudes, they are finite in the UV, and they're guaranteed to be so because of this exponential factor over here. This solves you, and it provides you with a sub behavior in the UV. So yeah, it seems to be that if you want to have some intuition of what's going on the UV-like sector of the celestial CFT, seems to be that string amplitudes are a really nice playground to start having some intuition.
Is that A?
Sorry. This A? Yeah, it's just sorry, it should be an alpha prime. So but it's just well, it's just some bunch of constants of the string amplitude.
is introduced to regularize the amplitude? or-
No, it's naturally appearing on the string amplitude. Yeah,
So, do you need the words celestial there?
sorry, here?
Yes.
No, yeah, it's true that you, this is also true on the momentum basis. The first string theory.
Wait a second, the two-level amplitude in conventional. let's
Yeah,
say,
in field
it's
theory.
finite, right?
Yeah. Sorry, you mean the gravity or the string theory? The
No,
gravity part.
That's the base, that's in
In
the.
field theory? Yeah, it's usually, or depends on the theory, right, that you're considering. But I think it's in most cases, most theories is also exploding. You're not UV well defined.
Okay, but just here.
The GR, just, okay, you do GR and take G mu, eta mu plus H mu. I never done that calculation on the UV, but I do think I think it's fine. I think. I'm not sure.
I mean, I want to understand the statement that this blows up. in
Yeah.
the-
Yeah, so you,
celestial base.
okay, yeah, so you start with the amplitude, you compute the Marin transform, so you mix up all the energies from the IR all the way to the UV, and you see that the blowing part is the infinite part of the interval. So yeah, if you want to, you don't have a true level for point gravity and amplitude because it's just giving you an infinity.
Right,
Additional
and
sum.
my question is, I'm wondering, well, if it is finite in, let's say, in the conventional field theory
Yeah.
case, then why do I care that it's?
Yeah, so we also know that if you do that in the case of DR, we know that it's not you cannot perform a so for instance, if you do a one loop calculation, you know that this is the one loop level, and it's gonna give you a higher contribution than the true level, so that's a problem even to start. So if you just start from GR. So yeah, it seems to be that just from the GR part, it's not consistent. So yeah, if we want to start from gravity, that's not a good start point. So yeah, here we're interested in computing what's going on and having some intuition on what's going on the to quantum gravity, right? So so wait, can you ask me the question again? I think I
Yeah,
forgot.
so,
when it
so,
was
okay,
asked.
so let me assume that the amplitude in the conventional Minkowski, say, space-time is finite, yeah, at tree level.
Okay, yeah.
I mean, I guess it's finite.
Yeah.
It's just,
But if you go on higher orders, the
No.
next order it's problematic.
forget about rules.
No, but even in true levels,
Okay.
because the constant,
So you're.
how the constant is dependent on 1/g. So if you take higher, or I just think it's g. So if you take higher point amplitude, the higher point.
But this is a four gravity.
Yeah. This is just true for the 4-point gravitational amplitude.
So now you transform this into the celestial basis.
Yeah.
Now you're examining the UV and you discover that this is
Yeah.
going up.
Yeah.
So I would say, well, this is just an artifact of the transformation. I mean,
Yeah.
Because in Minkowski, it's finite.
Yeah, that's true.
So my attitude will be not worried because I know it's finite in Minkowski.
Yeah.
And I don't care about.
Yeah, that is true. That's true. But
Let me just, but you're saying, well, people amuse themselves by saying, okay, there's something interesting in the UV and this can be corrected with string.
Yeah.
With strings.
yeah. See, yeah, that's true. So if you just want to study from the UV like behavior of quantum gravity, you cannot do it by just performing this Spartan amplitude. So this is one of the reasons why we use string theory to get similar amplitude. Right?
So would you say that because you have the cutoff, explicit cutoff of the Planck mass, you cannot just, take a explicit infinite UV?
You're saying on the garden?
Right, and if you do this combination of something, I mean, you have the cutoff there, right? So,
Yeah.
I mean, it's an effective theory, you cannot just take your energies up to the
Yeah.
sky,
Yeah, that's right.
right? So maybe, again, this natural fact of the fact that you're taking an integral up to infinity for your
Yeah.
energy basis.
Yeah, that's true. I don't know if people have done some sort of reduced Marin transfer with adding this UV factor, so this UV cutoff. I don't know if people have done that. But yeah, you're totally right. If you want to study what's going on in the effective field theory, we don't even need the celestial, doing the celestial transfer to begin with. So, yeah, that's true. Any more questions or comments? So, okay. So yeah, so that was one motivation on string theory. So let me now discuss the next motivation, which is now more linked with the calculation that we actually did in the paper. So there's the observation that if you start from string amplitudes and you take the alpha prime going to zero limit, you recover field theory amplitude. So this alpha prime is just a parameter that's recurrently appearing on the string amplitudes. So as a Hamburg argument to see that this is true, is to know that, okay, this alpha prime is proportional to 1 over the string tension. So if you take alpha prime going to 0, essentially you're taking the tension of the string going to infinity and thus having no string at all, but only point-like particles. So yeah, it's not weird that you're recovering for theory amplitudes. So now, of course, this is just a hand-wavy argument to see that this is true. However, there is a more mathematical and rigorous way to show that this is actually a correct statement. Okay, so now this is in momentum basis. And I've said before that, okay, you can go from momentum basis to the celestial basis by performing a Marin transform. So you can individually translate each corner into the celestial sector. So yeah, we can have the celestial string amplitude and the celestial field theory amplitude. So now the question arises naturally, right? Is there any way that we can go from celestial string amplitude to celestial field theory amplitude? So yeah, that's the question that we have to answer. The naive expectation is to, okay, just take the alpha prime to zero limit. However, we're going to see in a couple of slides that yeah, this limit is not consistent. It's not going to provide you with the correct restriction. Okay, so now the original work was done by Stewart and Taylor in 2018. They analyzed the 4-point true level amplitudes in the case of gluons and gravitons. And they found that if you take the forward scattering limit or the large R limit, where R is just it's called the conformal ratio. So it's just a function of the Z and Z bars. So if you take the limit, it provides you with the correct theory prescription. And there's also the work of the negative Gonzalez, Pullman, Rojas, where they study what's going on at one loop level. So they analyzed 4-point one loop amplitudes in the case of gluons. And they found that if you take a correct modular space limit, you recover Yang-Mills amplitude, one loop Yang-Mills amplitude. So yeah, however, the full picture is not that clear. For instance, if you start adding more external points, the number of these conformal ratios, so in the case of true level, also increases. So, so yeah, and also there's this other statement that was first noted by these authors over here, that you could also take different values of the R, and also those also provide you with the correct field theory description. So instead of taking large R, you can also take small r, so just R going to 0. Yeah, you also recover field theory amplitude. Okay, so yeah, now the full picture is not that clear. So we want to analyze what's going on the 5-point case. So 5-point true level amplitudes in the case of gluons. So yeah, in this case, you have two conformal ratios. So which one do you take to infinity? Which one do you take to 0? Do you take one to be constant? So yeah, that's the question that we want to analyze. Okay, so with this in mind, here's the most celestial picture that I could find in my phone. So this is just a fresco in Galleria Borghese. So yeah, let's discuss about the celestial string setup in order to do some computations. So I've repeatedly said that you can obtain celestial amplitudes by performing a Marin transform. And so here's the specifics, right? So you start with a momentum amplitude, which is given by these two terms. And you perform a Marin transform for each external energy that you have. So yeah, that provides you with the Marin amplitude over here. So the celestial amplitude. Okay, so of course we're working only on particles that leave and that enter and exit the parameters diagram on square plus and square minus. Of course, those are only massless particles, so we can use this null vector parameterization, which essentially rewrites the momentum in terms of some energies, omega, and some complex numbers, so complex variables, z and z bar, which are telling you the information of the position of these particles on the sphere. So of course, you typically parameterize the sphere with two angles, right? So what we're doing here is projecting these two angles into a complex plane. So this is just the name of it is doing a stereographic projection. And this eta over here is just telling you the information whether the initial particle was incoming or outgoing. So just a plus or minus. Okay, so we know how to obtain celestial amplitudes from momentum space. So now we have to discuss a little bit on how do we compute the string amplitudes on the momentum basis. So I'm gonna just do it at the surface level. So here I have a 4-point true level scattering amplitude. Okay, of course. So now the difference between standard amplitudes that we see in quantum field theory is that here we have a two-dimensional worksheet. So in FT courses, we see that we have typical S channel, right, which are just lines, which are described by point-like particles. So here instead we have surfaces. So we have to deal, how do we compute these surfaces? Okay, so yeah, unfortunately, we do not know how to compute the amplitude that is presented to you as it is. However, we can use symmetries to obtain simpler and calculable expressions. So in this case, we can use conformal symmetry to write down the left-hand side, which is, as I said, a 4-point true level amplitude, labeled by its 4 choices of momenta, so B1, B2, B3, and B4. We can map that into a sphere with 4 insertion points, so B1, B2, B3, and B4, presenting the exact same topology. So yeah, calculating the right-hand side is the equivalent of doing the left-hand side. So now, fortunately, we do know how to compute this side over here. So now let me quickly shift our attention to understand how do we do that. Okay, as I said before, this is a sphere with 4 insertion points. We can parameterize each insertion with an angle, or we can just say it's a parameter and we call it x. So naturally, since we're working in a quantum theory, of course, we have to take into consideration every single possible insertion. Because yeah, this is just a property of the quantum theory. So in other words, we have the freedom of these parameters to be moving around the sphere. Okay, so this mathematically translates of computing 4 integrals. So now this is quite difficult to deal as it is. Again, we can resource into using symmetries to reduce the difficulty of the problem. So in this case, we have SL2R symmetry. So this symmetry allows us to fix 3 of the 4 insertion points. So yeah, in other words, the only one free to be moving around is this, sorry. So yeah, the one, yeah, that can be moving around is this P1 over here. So this translates to the level of the amplitude over here. Instead of computing 4 integrals, we just have to compute 1. Of course, this is the story of 4-point amplitudes. So now the 5-point case is quite similar. So instead of having 4 insertions, we have now 5. So instead of having 4 integrals, we have 5. And again, we can resource into SL2R symmetry to fix 3 of the 5 integrals. So yeah, this is essentially what we're gonna what we have to deal with. So just a double integral of some weird functions that I'm not showing you here. Okay, so this is just a string amplitudes 101. Okay, so now moving on into the specifics, we know that the true level maximum helicity violating amplitude for equals 4 and 5 gluons in the type 1 superstring theory follows this factorization. So yeah, just a pretty nice factorization going on, where these we have some Gabriel's term given by the Parcello formula that I have over here, written in terms of the sphere helicity variables, corresponds to these triangular numbered brackets. And we have multiplied by this string factor, so this f, which is the one that's going to be carrying around these integrals that I was showing you before. And we choose this Mandel subincurrent, so this Sij. We write it in terms of this null vector parameterization that I showed you before. So we can put it in this really nice, easy, and compact form. Okay. So now here's the specifics. So we have the string factor with a smaller definition for the Mandel subincurrent. So we're picking this neighboring selection for the S's. So here's the full expression. Of course, this is quite cumbersome to see, especially at first glance, right? However, I can tell you some really nice properties about this expression over here. So first, we can see that we have a double integral to be computed. So yeah, this is the integral after doing the SO2R fixing that I was telling you before. And we also have a non-trivial version of this also alpha prime, right? Because it's on every single exponent of these x and y variables. Okay, it's put in a very non-trivial way. And we also have an overall alpha prime square factor. Okay, but essentially we can write down the fat Gluon string amplitude in momentum space. So yeah, we can theoretically go to the Marin space. We're performing this Marin transform. So that's what we did. And we obtained this string amplitude. Yeah, we obtained this expression, which is, again, it's a little bit cumbersome to see. However, there's a really nice property going on. So now you can see that this alpha prime dependence is completely factorized out of the integral, and it's put in this very trivial form. So we just have alpha prime to the beta, where beta is just a function depending on the deltas. So it's just the imaginary part of the sum of the deltas. So, okay, so you can immediately see that if you take the alpha prime limit, which is the naive expectation, right, we just obtain a flat zero. Okay, so we also have some combination of some conformal ratios, which here have the expression. We have some z bars, and we have a double integral of some weird functions, right? So now these f's and c's, they're just functions of the z and t bars, and this a over here, which is right on the end, it's just a function of the z bars and the logarithmic combination of the x and y's. Okay, so we essentially can write down these as string amplitude. So now let's move on to the exploration to find, if any, its field theory limit.
Sorry.
Yeah.
What was beta?
Yeah, so beta is just a combination of just the sum of the deltas, the imaginary part of the deltas.
So this is an expansion of alpha prime. This is the
No, this is a full expression. Yeah. Yeah.
So what happens if you take alpha prime to 0?
So if you just take alpha prime going to 0, you obtain just a you don't obtain the correct amplitude.
So match with let's say perturbation theory in
Yeah, you want to match it with the Young-Mills amplitude. That's equivalent to this on field theory. So 5 gluon amplitude from Young-Mills. That's what you want to recover.
Is that double integral impossible to compute?
I think you cannot put it in a closed form. I think, at least Mathematica can do it. And I'm pretty sure people don't know how to do it either. So yeah, I wouldn't say that you can complete it exactly.
You can do that integral like going around.
Sorry?
You can do computation.
Yeah, that's exactly what we're going to do. We're going to see some limits to reduce the difficulty of these integral.
yeah. This is the full thing at 3 level.
Yeah, 3 level.
Without forms.
Yeah. Yeah. You can do it at loop level. I think you have an extra integral on Q, right? So, but yeah, this is the loop level. Okay. So yeah, let's find let's go to exploration to find its field theory limit. So here are some suitable candidates. So we have the Bredger limit, soft limit, collinear limit, forward scattering limit, hard scattering limit. Okay, there's this more suitable candidates also to be considered. However, we picked the Bredger limit. There's a whole story with the Bredger limit and string theory that I'm not going to discuss. So, however, when you consider high point scattering, they branch out roughly into 2 categories. So you have single and multi-Bredger limits. So the first one is just taking one of the internal energies to be dominant over the scattering process, and the second one you allowing more than one energy to be dominant. Okay, we picked the first statement, so we picked the single Bredger limit, which spoiler is going to give us the correct field theory prescription. Okay, so here's the single Bredger limit, quick 101 basics. So we have the neighboring selection of the S's. So of course, since we have 5 external particles, we have 5 S's. So we also need this further definition for the momentum. So in order to this formula to make sense. So it's also very convenient to define this quantity over here. So kappa, which is defined in terms of S2, S3, and S5. So now we take S1, S2, S3, S4, and kappa to be the 5 independent momentum variables. So as a little reminder, when you have an endpoint scattering process, you in general have 3n minus 10 independent momentum variables. So if here we have n equals 5, so 3 times 5 is just 15, minus 10 is just 5. So yeah, from these 6 selection over here that we have on the top, we have to just pick 5. So yeah, this is just one of the multiple possible choices that we can do. Okay, so now the single Ricci limit is this statement over here. So we take S2 going to infinity, and we hold S1, S3, S4, and kappa fixed. So if you see the definition of the kappa, if you take S2 to infinity and you want to hold this expression to be constant, you also need S5 also going to infinity, which is totally okay because it's no longer one of the independent variables. So yeah, this expression has been studied extensively in momentum space. However, it's not very friendly to work in the social basis. So with a little thought process, we can translate it into some set of kinematic collinear limits. So we just take S1, 2, S3, 4, so Z3, 4, and Z4, 5 into 0. And implicitly, we're also taking the same limits for the Z bars. So when we do that on the celestial string amplitude, we obtain this expression, a leading order, which is exactly what you would have obtained if you take the 5-point gluon amplitudes from James's theory. Even at the constants, they're exactly the same. Even these 2 pi and the direct function. Okay, so we also noted that you can you could also take a more general limit, which is just taking the Z12 going to 0 limit, and we obtain the exact expression. So then we say that the most general limit that you can take is just a single set of kinematic collinear limits. So here shortly, I present you with the collinear table, as I like to say. So here on the left-hand side, we have some collinear limits, and on the right-hand side, we have the x and y dependent integrants that's going directly on the celestial string amplitude. So yeah, we only analyze the first line. However, it could be nice to see what's going on what's the hierarchical behavior of these other limits. For instance, we could obtain the 4-point string amplitude from one of these candidates and taking a suitable tangent variables. Okay, so now to finish, because I'm past over time. We successfully analyzed the field theory limit, where we found that a set of kinematic collinear limit inspired from the single Ricci limit provides you with the correct field theory prescription. So of course, this is not, as I told before, this is not the most general one. So the most general is just taking the Z12 into 0 collinear limit. So now the question remains, the remaining question is, okay, is there any generalization of this result? So unfortunately, it's not that clear because of the increasing complexity. When you start going to a 6-point string theory or even n-point, you don't have a really nice factorizations for the string amplitude. And sometimes the string factor is not possible to put it in an inequal form. So yeah, the generalization is not that clear. However, I do think that the limit should still remain on the kinematic sector, which is something really strong to say. And also we computed these two other topics in the paper that I didn't have time to discuss. So here's just a flash summary. We also computed the conformities of term. So it's a really nice factorization when you compute the what's going on the infrared limit. So here we see on the left-hand side a 5-point string amplitude, and on the right-hand side a 4.1, which is quite nice to compute and to put in a simpler equation, at least the 4.1. You can use the Venetiano amplitude. And we also discussed the map between the puncture string worship CFT and the puncture celestial CFT. We did it in the case of gravity for gravitons. So in that case, we have this interval to be the amplitude. So in this interval, we analyze it at the hard scattering limit. So if you take every single S, the minus of variables to go to infinity. So when we do that, we obtain that the solid point equations of this interval are given by this expression, which are known to be the scattering equations. So are key formulation in the there are key equations in the catastrophe and Yuan, or just CHY formulation of scattering amplitudes for massless particles, which they naturally appear on the infrared limit. So yeah, we're seeing a very nice matching between low energy and high energy. So yeah, now the punchline is that a single configuration of a momenta of a closed string gets mapped into a minus 3 factorial possible vertex operated configurations. So yeah, this is the end of my presentation. So thank you very much for your attention. And I'm happy to take any questions if you have.
Thank you, Gabriel. Anyone, any questions? Please.
Sorry.
Yeah.
Can you explain what does mean by that worksheet that you was talking about for the momentum type, momentum in space? Well, so what are the computations that you need to do in the cases? What are the amount of computations?
Here, right?
Yeah.
Yeah, so you need in some sense to compute okay. You have any chart? Right, in a standard KFT textbook, you study this diagram, right? Sorry, right? So this is just some word lines of some point-like particles, right? So this is what you have lines. So here instead we have a two-dimensional object, so a string. So instead, so this is just the word line of this two-dimensional case, which is the case of string theory. So in some sense, we have to know how to compute the area of this surface over here, but we don't know how to do that. So yeah, that's why we use conformal symmetry to parameterize the sphere, the 4 insertions.
That is why you are considering D plus 2 to the dimension. You are like.
Oh, no. That's a statement on the celestial point of view. So wait, you're confusing it with. No, this is open strings. You can also do the case for closed string. You have something like this. Gravity is closed, but we're not analyzing gravitons. We're analyzing gluons. Yeah. Sorry. This, right?
Yeah.
No, this is just a statement for the group theory point of view.
Oh.
It has nothing to do with the number of dimensions that you're working on the string theory. So here, we probably have heard that string theory have many dimensions, right? So here we're just taking every single extra dimension as a difference from the 4D dimension space, as they're not playing any role, so they're just turned off. So yeah, it's just an interesting note.
Okay. Go ahead.
There is a conjecture that thought that there is this dimensional reduction in quantum gravity that's effectively 2-dimensional. I don't know if you know about this.
No, unfortunately, I don't know it. Maybe you can explain
I
it.
don't know.
Okay.
I do know that there is this conjecture, and some people like Stephen Carley and so on and so forth take it seriously. So I wonder if this is an instance of that. It's hinting to the fact that intrinsically quantum gravity is a 2-dimensional system.
Yeah, I mean, maybe that's the spirit of studying the celestial calligraphy. Yeah, I mean, probably because okay, so you have okay, so maybe it's something going on with 2 dimensions, right? From that point of view, and string theory is sorry, the celestial calligraphy is just a problem. Okay, we're seeing that we can reduce holographically 4 dimensions to 2. So maybe that's the original original idea of why doing this much. Maybe. No.
I do have another question. You showed the triangle and you mentioned that there should be, or there could be some cosmological triangle.
Yeah,
Do you know anything about that? Is anyone doing anything about that?
that's a great question. I have no idea. Maybe we can fill it up. So wait, let's go in so slowly. So this, right? So yeah, maybe, so this side, I know that's related to these, some squeezed limits, right? Which is analogous to taking the cosmological software. So yeah, I don't know if we can move it on to show some observable on the right-hand side and some symmetries on the top. I mean, this could be only done, if I think about it, this is could be only done at the level of the cedar, right? We need to study more about the asymptotic symmetry of the cedar. Which is quite rough to do. Maybe it's more easier to compute this side. So the observable point of view. Yeah. But it should be interesting to compare what's going on the cosmological sector. Definitely.
I'm asking because you went to this summer school and
Yeah.
you're part of the community.
Yeah. So people always say, okay, this could be very nice to do, link the social holography program with the cosmology. So a lot of people are trying to say, oh, we should do that. But I don't think has been any progress in doing that. I would say because of it's very rough to study what's going on at the boundary of the cedar. So because sometimes you don't have a boundary. So yeah, I think this is something that we can ask ourselves. Okay, maybe 20 years later, where we have more intuition of what's going on in the cedar. Yeah, so that's a very nice question. Go.
I didn't understand very well why you're interested on those links that you mentioned.
On those, the Raggi limits?
Yeah, on the other ones.
I mean, it could be interesting to analyze the other ones, for sure. For instance, the high scattering limit, we analyze it in the case of gravity. We are seeing like these very nice scattering equations popping up. However, we also computed them in the case of gluons, but we didn't find anything that sparkles out from that expression. So yeah, we didn't analyze every single one, but yeah, that was the most interesting one to see. So the single region.
So, any more questions? Okay, if not, let's thank again to Gabriel. And since the pizzas are here, we can go.
Don't know.
That's a nice question. ¿Dónde?